Hey everyone, how's it going? Hey MS, how's your day? Bored. Okay, well, let's try and change that. Camera's lagging. Okay. Let me take a look. Okay. Seems to be fine. Sweet. Yeah, it's probably just it's getting up and running. Yeah, let's try and fix the being bored with some physics. We're doing energy levels and excitation in atoms, which is like a pretty fundamental topic. Hello to India. Best revision advice. Sorry, for AQA A-level physics. Yeah, I mean, it depends what stage you're in, for sure. I guess at this point we're getting closer to exams and tests and stuff. So I think the most important thing now, personally, is to not spend too much time on stuff you already know. It's easy to kind of, it's like quite comforting, right, to kind of read over the things that you already know for sure. But there's a couple of good methods for finding the things that you're struggling with the most. I like to do a practice paper. Once I've done the practice paper, you know, I know my mark and I could just stop there, right? Now I know how I'm doing. But practice papers are better than just telling you how you're doing. They're pretty useful because they tell you everything in particular that you got wrong. So I make a list of each topic that I got a question wrong on in a past paper. And then I go to my revision books or my revision videos or textbook and just look at those bits. And I tick each thing off that I wasn't able to do in the past paper. And then I do another past paper and do the same thing. The point is I use the past papers to figure out which things I should study. Yeah. But in particular, using the papers to figure out which bits you need to then go look. Yeah, excitation is well, it's sufficiently fundamental. It's basically just about, it's one of the most important things to know about how atoms behave. And that's important in chemistry, because it's important for deciding how, or for figuring out how different atoms are going to react with each other. But it's important in physics as well. Oh, I'm glad it's good timing. It can often be quite a confusing one, especially the absorption and emission spectra, which again comes up in chemistry, right? So the people of you doing chemistry, you'll have seen absorption spectra and emission spectra before. But in physics, we also care what things are made of. We care about finding out what things are made of. But yeah, this is that kind of bit of science where physics and chemistry overlap quite a bit. This stuff, and also a lot of stuff about ideal gases. That's another place where physics and chemistry overlap quite a bit. There must be others as well. Yeah. Those are the two main ones I can think of. Yeah, chemistry is much more focused on how atoms interact with each other, by which I mean how they react with each other. But of course, when we're doing physics, we need to know what things are made of, and a lot of chemistry is really important for a lot of physics, and the other way around. Whether you do, if you were to go on and do a degree, physicists and chemists learn quite a bit of similar stuff, especially in the first year. Okay. So I'm just going to get us set off. Hopefully everyone can see the notes now. And now we'll get ourselves started. So today is about energy levels and excitation, which, as we were just saying, is as much a chemistry topic as it is a physics one. But that's great. That means we're covering more bases. So about me, this is me before I tried cutting my own hair. Head of physics at Spectra, currently doing a PhD at Oxford, also hanging around a bit in, well, before the lockdown, I was hanging around a bit in UCL as well. It was kind of split between the two. And yeah, been an A-level physics tutor for at least the last 4 years now, maybe more, including doing this for a year or two. Yeah, I do look different, right? Yeah. But still hopefully recognizably the same person. I promise that is me. Okay. So if you enjoy, well, even if you don't, but especially if you enjoy what we do today, you can get one week free trial to check out a lot more of this stuff, which is just on the Snap Revise website. So I'm doing this web class here. I also do another free, and there are another, altogether there are another kind of 3 or 4, maybe, yeah, 4 physics sessions a week just on the Snap Revise website. So this is just a little snippet of all the stuff we're doing. And if you want a 1 week free trial of all of that, you can enter this code at the checkout on the Snap Revise website. Good, okay. So let's get ourselves started. Today, our objectives are to understand how electrons in atoms are organized in energy levels. So this is key. This is essentially what defines the different atoms. Okay, we're going to calculate the energies of photons emitted during excitations. This is the key property that we can use to figure out which atoms we actually have in some kind of substance. And we'll see that when we look at the absorption and emission spectra, which is part 3. Although things will be spread out slightly differently during the session. Okay, so let's get going with the material. And the first thing I want to do is cover a couple of things that we're going to need to know to actually get through the session today. So the first thing we need to know about is the electromagnetic spectrum. So the first thing I like to ask, just as a warm-up on the electromagnetic spectrum, yeah, we will come to that, is it would be good if people could tell me the elements of the electromagnetic spectrum, so things like infrared and ultraviolet, starting with the longest wavelength, that is the smallest frequency. I'll give you a hint. The lowest frequency one of all the waves in the electromagnetic spectrum is the radio wave section. So does anyone know what happens after radio? Radio, micro, good. Next one is microwaves. Good. Not bad if you don't know, that's fine. You can pick it up here. Okay, good, yeah, infrared. I like that. I'll just call infrared IR. So this one in the middle, which is split up into all of the different colors of light, is the visible light. Good. So there's visible. Okay. Next, we've got ultraviolet. Good. Which I'll just call UV. What else have we got? X-ray. Perfect. And finally, good. Yeah, I can see that on there as well. Gamma rays. And as I said, we were wanting to start with the lowest frequency or biggest wavelength. So here we have low frequency. And up here we have high frequency. Okay. Now I'm talking about frequency because the things in the electromagnetic spectrum are waves. And waves have frequencies and they have wavelengths. Good. Okay, so you can think about the things in the electromagnetic spectrum as being waves, but we can also think about them as being particles. And we call the particles in the electromagnetic spectrum, that is kind of particles of light, we call them photons. So these are particles that kind of make up light. And there is a formula for figuring out the energy of the particle that represents light, the energy of a photon, given that we know its frequency. And I think I already saw it, but I think it's gone off the chat now, actually. So how do I find the energy of a photon? If the light that it represents has frequency f, good, then the energy is given by hf, where this h here is Planck's constant. Okay, which you'll be able to find in your formula book. So frequency is measured in hertz, which is the same as seconds to the -1, and energy is in joules. Okay, so the last thing we need to know, hey Phil, how's it going? The last thing we need to know is the definition of an electron volt. So an electron volt is a measure of energy. Yeah, I'm not actually sure of any good mnemonics for the elements of the electromagnetic spectrum. If anyone knows any, feel free to put them in the chat. Okay, so 1 electron volt is one particular unit of energy, and it is the energy required, so I'll put that here, energy required to move 1 electron through a potential difference. Let me retype that. A potential difference of 1 volt. So to find out what an electron volt is, then what we need to do, it's not quite the work function, no. Good. Energy gained by an electron when passing through 1 volt. Yeah, absolutely perfect, Bohemian. Cheers. Okay, now this is actually pretty convenient to figure out then. So we know that the energy required to move some charge through some potential difference is the charge multiplied by the potential difference. Here, we're saying that the voltage we move through is going to be a voltage of 1, and the charge is going to be the charge of an electron. So altogether, 1 electron volt is actually just the charge of an electron in joules. 1.6 times 10 to the -19. But now, rather than being coulombs, it's joules. So that there is the charge of the electron, but now in joules. Good. Okay, so that's the stuff we need to know to get through the session. So I'll just mention what the spec points are that we're going through for each exam board, because some of you will be on AQA, some of you will be on OCR, and some of you will be on EdXL. But we're covering spec points for all of them here. Okay. One of the classic things we're seeing here is E equals HF, and the stuff we're going to be looking at is this spectral line stuff at the bottom. Okay, good. Okay, so the first thing we're going to be talking about is energy levels, or electron shells. They're essentially the same thing. So there's a lot of kind of tripping over words here. So I'll start with the definition, and I'll kind of explain what we're talking about as we go through. So here's the first statement. The first fact we need to know about atoms are that electrons in atoms exist in special shells which correspond to energies. Each shell or energy level represents the energy that an electron will have at that level or shell. So let me just put energy level in quotes there. So when we have some kind of an atom, usually we imagine, so here's my atom, that there are electrons around the outside. What we have to remember is there is only specific places where the electrons can be. They could be at, for example, this ground level here, or they could be at what's often called the first level or first excited level, which typically involves the electron moving further away from the nucleus of the atom. So we call the bottom level the ground level, and I'll write that here. Sometimes called the ground state as well. And sometimes that's given the label n equals, sorry, yes, I should have called this the second excited level. So often we call this n equals 1, then we call the next level n equals 2, n equals 3, n equals 4, n equals 5, and so on. Now there's gaps between these energy levels, and these represent the energy required to move from one energy to the next. Does anyone happen to know for hydrogen what the energy of the ground level is? They're all written in minus signs. The second level is 3.4 electron volts. Now you can see why we've stated things in terms of electron volts. We stated things in terms of electron volts because then they become nice numbers. Like in joules, the second level is like something horrible. It's something times 10 to the minus 19 joules or whatever. But in terms of electron volts, it's 3.4, which is not very many, which is like a kind of an easy to talk about number. Good, so the ground level is minus 13.6 electron volts, good. And you definitely don't need to, minus 13.4, yeah, almost. And then we can go further up, 1.5 electron volts, minus 0.85 electron volts, and minus 0.31 electron volts. Now, the key thing to notice about these energy levels is that something happens as you move further away. As you go further up the shells, the energy gaps become smaller. The gaps between the energy levels become smaller. So for example, the gap between n equals 1 and n equals 2 is what, 10.2 electron volts here. Whereas the next one looks like it's about 1.9, maybe 2.9. So the gaps get smaller and smaller. They're in minus so that we can call being infinitely far away from the atom 0. So this is just a convention. They could have been anything. But the convention we choose is that if an electron has escaped from an atom, it then has an energy of 0. So we often call this the n equals infinity level, to kind of express that that an electron has managed to get infinitely far away from an atom. And we ask for this to be an energy of 0 electron volts. Essentially what what an energy of minus 13.6 electron volts means is that you would need 13.6 electron volts to get the electron out of the atom. So originally my electron is here, and I need 13.6 electron volts to get out. That's why I currently have negative 13.6 electron volts. Okay, what do we call it if we manage to get an electron out of an atom? That's like a very specific process, which again, you talk about a lot in chemistry. Absolutely right, it's ionization. Yeah, if I manage to remove an electron from an atom, that's ionization. So this energy here, 13.6, is the energy I need to ionize hydrogen when the electron is in its ground level. Okay, so let's talk a bit more about these electrons moving between these levels. Let's say I have an electron which lives at this first level here, n equals 1. I can talk about the energy required for it to move up to this level here, and the energy is given by the gap between them. So electrons can move up energy levels by gaining energy. Specifically, gaining enough energy. to do so. So here, if I give an electron in the ground state 10.2 electron volts, then it will be able to move from the ground level up to the second level. Good. Okay, so how can I give an electron energy? Like if I've got an atom in front of me, how can I give an electron energy? Well, there's two main processes. First is that the electron might absorb a photon. The second is that something could collide with the electron. Absolutely right. So we need to absorb a photon if we're going to move from one energy level to another. Now, what's interesting is that these two processes actually behave kind of differently. What I mean by that is that if I want to get an electron to move from the ground level up to the first level, the photon that's absorbed by this electron needs to have exactly the right amount of energy, by which I mean it needs to have exactly the energy gap between the first and the second level, which is here 10.2 electron volts. On the other hand, if I try to excite this electron by bumping some other particle into it, so this is point 2 here, let's call these 1 and 2. I could have some particle P, which I get to bump into the electron. Here's my particle P bumping into the electron. That could give it enough energy to move up. But even if it had a bit more energy, even if it had like 10.4 electron volts, that would be okay. That would still make it possible for this particle to bump the electron up to the second energy level. Exactly. Whereas if the photon energy was slightly higher, this transition just wouldn't happen. So what happens to the spare energy? Exactly. So with a photon, if I have a photon here and it has 10.4 electron volts, when the gap is 10.2, the photon just won't get absorbed. It will just go through. However, if I have a particle, like a general thing, like for example, another electron that's flying through and it bumps into the electron and it originally had 10.4, then what it can do is it can give this electron 10.2 and it'll just bounce off with the remaining 0.2 electron volts. So there's a difference between absorbing a photon and bumping into some other particle like an electron. And that's the key thing we need to kind of be aware of here. Yeah. We'll actually see an exam question about that point. So yeah, keep that in your head. So now we can talk about the kind of experiments we can do once we know this stuff. Yeah, no worries. Now we know that when we aim photons at atoms, they will only absorb specific frequencies. Remember, all the other photons would just pass through. We can use this thing that we know about atoms to figure out what atoms are actually in some random substance. So here's the idea. I'm going to have some substance here. And I want to know what it's made of. I want to know what atoms are in there. And I can figure that out using absorption spectrum. So here's how it works. First of all, I take a cool gas. So my substance needs to be a cool gas. And then I send white light through it. Now, what we know is that white light is made up of all the different frequencies. White light is a mix of red light, green light, and blue light all together. However, when white light is sent through the gas, so here's white light with lots of photons of lots of different frequencies being aimed at it. Only specific frequencies will be absorbed. So that's what we saw back in the previous part of this. I was saying, okay, with electrons, it's different. But if I'm firing photons, if I'm firing light at an atom, then if the photon has the wrong frequency, it won't be absorbed. But if its frequency is exactly equal to one of these gaps, then it can be absorbed by an electron. So if we go to this picture now where we're sending all different frequencies of photons through a substance, specific ones will get absorbed, but the rest will pass through. So for example, here's frequency 1, frequency 2, frequency 3, frequency 4 being sent through. Maybe all of them get through except for frequency 2. And what that's going to cause is some kind of a gap, something that we can't see on the other side. So if we now look at this light on the other side, so here's an eye kind of looking at the other side of the gas, then what you'll only see is 3 of the frequencies that were sent through the gas, with one of them missing. And that will tell you what energy levels there must be in the atoms in that substance. So we have to do a bit more than this when we're actually doing the experiment, because at the moment all this light is kind of clumped together, and what we need to do is to spread out this white light once it's gone through the substance so that we can see all of the colors in it individually. So if I have white light all kind of bunched together and it's a mess of different colors, does anyone know what I can send that white light through to spread it out into all the different colors of the rainbow that it's made of? There's a very simple kind of object that I can pass white light through that will make the light spread out. Yeah, perfect. I can send it through a prism. So at the moment, all this white light is bumped up together. But if I send this light through a prism, absolutely right, then this will create a spectrum in which we will be able to observe missing frequencies. And that's exactly what we see here at the bottom. So what we're seeing here at the bottom is what we would get if we put white light through a substance and then spread it out with a prism. We get an absorption spectrum. Which is a spectrum with some missing frequencies, which tell us what the energy gaps in the atoms must be. Good. And this spectrum can be used to figure out what energy gaps exist in the atoms in the substance. And since different atoms have different energy gaps, that can be used to figure out what atoms are in the substance. So this spectrum can be used to deduce the energy gaps for atoms in the substance and so identify the atoms in the substance. Great, absolutely right. Triangular prism. So this is actually really useful, and this is really useful for chemistry as well, which is why you guys were mentioning a lot of chemical. Like all the time in chemistry, you need to know what your substance is made of, and this is how you can do it. Once you know how atoms work, once you know how energy gaps work, you can use absorption spectra to figure out what atoms are in your substance. Okay, so how's everyone feeling? How are we doing with this stuff we've just gone through? Okay, cool. Ones and twos. Hey, how's it going? Okay, ones and twos. Awesome. Let's have a go at some questions. So the diagram shows 5 electron energy levels of an isolated atom. The ground state and the ionization level is infinitely far away apart. No worries. Cheers. Okay. BI. An electron with kinetic energy 2.6 times 10 to the minus 18 joules collides inelastically with an electron in the ground state. State which energy levels may be occupied following this collision. So we've got an electron here, and we've got some other electron with some certain amount of energy, 2.6 times 10 to the minus 18 joules. And our question is, what levels can this electron be bumped up to? So what do we reckon? Have a guess in the chat. Can it be bumped up to level B? Can it be bumped up to level C, level D? Okay, so we can take a look at the difference in energies between these energy levels. Absolutely, yes. So we actually will be able to get up to C, and we'll be able to get up to B as well. So the difference in energy levels here is 2.2 times 10 to the minus 18 joules. The electron coming in has more energy than that. So we can absolutely get up to this first energy level. What about the second energy level? Well, the second energy gap here is 4.6 minus 2.1. So this is a gap of 2.5 times 10 to the minus 18. However, this gap here up to level D would require an energy of 2.7 times 10 to the minus 18, which is too high. So we have enough energy to get to between C and D, which means we can get up to B or we can get up to C. Notice that in particular here, this is not a photon coming in. This is when we have some other particle like an electron that comes in and collides. So now let's have a look at another example. This time we're told a photon of energy 2.6 times 10 to the minus 18 joules is incident on an electron in the ground state. So here's a photon coming in with 2.6 times 10 to the minus 18. State and explain what would happen. So in this case, what would happen? What do we reckon? What energy levels would it get kicked up to? Would it get kicked up to any energy levels? Good, absolutely right. Nice. Do you remember I said that we had enough energy? 2.6 was enough energy to get between C and D. None of these energy levels, none of these gaps are exactly 2.6 times 10 to the minus 18 joules. This gap here is 2.5. And I guess the one above it was 2.7. None of them are exactly 2.6. And so the photon's just going to pass straight through. The photon will pass through since there is no gap of size 2.6 times 10 to the minus 18 joules. Photon's energy is not absorbed. Perfect. Nothing. Stay in the ground state. Yeah, perfect. Really nice answers. It wouldn't move at all. Great. Really nice stuff. Well done. Okay, so far, everything we've talked about involves moving up to higher energy levels, right? We're always talking about absorbing energy to go up to higher energy levels. This time, we're going to go the other way around and talk about emission, which is sometimes called fluorescence, which is also sometimes called de-excitation. So those are three different words. So let's imagine we have some electron and we gave it some energy. So it exists currently in some kind of higher energy, higher level state. These excited electrons don't actually want to live in these higher level states. If you leave them alone, eventually they'll fall back down to lower energy levels. But if they want to go back down to having lower energies, they need to get rid of their energy somehow. So does anyone know how an electron gets rid of its energy as it moves from a higher level down to a lower one? So excited electrons will eventually, if we leave them, move back down to lower levels. How will they do this? Absolutely right. They will emit a photon. Good. Just like they can absorb a photon to move up, they can emit a photon to move down. So if an electron moves from n equals 3 to n equals 2 here, then it will emit a photon of energy given by the gap between them. So the gap has size 3.4 minus 1.5, which is equal to 1.9 electron volts. So a photon of 1.9 electron volt energy will be emitted in this situation. It de-excites by emitting a photon perfectly. And sometimes we're not interested in the energy that was emitted. Remember, we were interested in look at these absorption spectra, and it's often more natural to think about colors of light in terms of frequencies. So we want a way to convert between frequencies and energies. So this lost energy, which will be emitted as a photon, corresponds to a particular frequency. That's a particular frequency in the electromagnetic spectrum because it is a photon, a particle of light. And the frequency is given by the equation E equals HF. So where this E here is the energy gap. So we can find out the frequency of this photon, which in this case would be 1.9 times 1.6 times 10 to the minus 19 to convert it into joules. That would be the energy, and then dividing by Planck's constant. That would give us the frequency of this photon. Can we say light? When we emphasize that we're talking about a particle of light, we call it a photon. So light, we might think of as either a wave or a particle. But when we say photon, we kind of say that we're thinking about a particle. What do I mean emits a photon? It emits a particle of light, a little packet of energy, which corresponds to a certain frequency of light. Good. Okay, so just as we can look at these absorption spectra we spoke about before by seeing what frequencies of light are absorbed by cool gases, there's another method for figuring out what kind of atoms make up some kind of a substance. This time, we're not going to pass light through it like we did before. Instead, we're just going to give it energy in some other way and take a look at what light is directly emitted from it. No, I actually mean it emits a photon. It is the electron moves, and what the electron emits is a photon. But it's just a pure normal photon, and a photon is a particle of light. Exactly. Yeah, good. So I wouldn't say light here, just because we're emphasizing that it's like a particle of light. And when we're talking about a particle of light, we call it a photon. Cool. Okay, so here's experiment 2. we get some kind of a gas and we excite it. Now we have to explain how we're going to excite this, although this won't be so important actually in exams and so on. But just so you know what's happening, because I think it makes things clearer. This time, like I said, rather than passing light through the substance that I want to examine, I just excite it. I have to give all of the electrons in their energy somehow. And one classic way to do that, if you're wondering, would be, for example, to heat it up with some kind of a flame. If you heat up a substance, you give all the electrons in the substance energy, and then those electrons will rise to higher energy levels. Now, when they're left alone, eventually they'll fall back down. And when those electrons fall back down to lower energy levels, then they will emit photons. And these will be the photons that we see. Again, we'll pass them through a prism to spread out the different colors. But this time, all we're going to see is the frequencies that correspond to the energy gaps in these atoms. So let's go through this properly now. So the light from an excited gas, so I've excited a gas by giving it some kind of energy, will only consist of certain frequencies. Which frequencies will it consist of? Well, it will consist of the frequencies which correspond to the energy gaps between these energy levels. I can emit a photon of this energy, of this energy, of, for example, the energy gap between n equals 3 and n equals 1, I could emit a photon of that size, but I can only emit these very specific frequencies, and I can't emit anything in between. Just like we can't absorb anything in between. So as a result, when we spread out this light, when we spread out the light that's being emitted by a substance, there's only some very specific parts that are actually going to exist. There's only specific bits of the spectrum, only specific colors of light that are actually being emitted. So what we're looking at here is what we call an emission spectrum. Let's underline that, as opposed to an absorption spectrum, where instead these bands would be missing and you'd have lots of color where all the black is instead. So it's like you've just inverted where the colors are and where the black is. Good. So this light can be used to produce an emission spectrum. With discrete, and by discrete we just mean small parts, just little chunks with discrete strips of color. And with these colors that we see, we know each color is some frequency, and from the frequency we can figure out the energy gap, because the energy gap is given by h times the frequency. So this spectrum can be used to, again, just like with absorption spectra, replace that, can be used to figure out energy gaps in the substance, and so find out the atoms it's made of. Great, so we can go both ways. So exactly, we have a load of excited electrons in our substance, in all their different atoms, and they will fall down on their own accord. And when they fall down on their own accord, they emit the frequency given by the energy gap that they fell through. And there's only specific energy gaps for each atom, and they're different energy gaps depending on which atom you're on about. And so only specific frequencies will be emitted, and you can use that to figure out what atoms are actually in the substance. So, how are we feeling? After this, we'll just we'll go through a couple of questions. Yeah, great. Okay, a couple of ones. Awesome. Let me know if you have any questions. But for the meantime, let's have a go at some exam questions. But yeah, let me know if there's anything you didn't understand from this, and I can have a go at answering. Cool. Okay, question 2b. The lowest energy levels of a mercury atom are shown in figure 1. The diagram is not to scale. Okay, so here's our diagram. We have a couple of different energy levels. We have quite a weird feature here. Usually, the energy levels get closer together. You might remember from the original stuff we looked at. They get closer together as you get further away. Here, this is a particularly weird atom where the energy levels actually get a bit further apart again from n equals 3 to n equals 4. But anyway, 2bi, calculate the frequency of an emitted photon due to the transition level n equals 4 to n equals 3. So originally we have an electron here. They're saying, imagine it transitions down to the energy level below. What is the frequency of the emitted photon? Okay, so how can I figure this out? What do I need to know? Oh, the box on my face is blocking the question. Oh, no. Okay, yeah. One sec, let me see. Oh, yeah. So it's a transition from, I'll write it here, from n equals 4 to n equals 3. Good, absolutely right. So we need to find the energy gap. So the change in energy between level 4 and level 3 is given by 0.59 minus 0.26. And at the end, we need to make sure we get the right units, which is times 10 to the minus 18 joules. So 0.59 minus 0.26, that gives us 0.33 times 10 to the minus 18 joules. Perfect. And once we know the energy of the emitted photon, so we have a photon here with a specific energy, we know we can figure out its frequency using the formula E equals HF. So in turn, that means F is equal to E over H, where H again is this Planck's constant that you can find in the formula book. And in particular, and I've seen it in the chat, so that's great, Planck's constant is equal to 6.63 times 10 to the minus 34. Good. So you should be able to find that in your formula book. 6.63 times 10 to the minus 34. And the energy we already know, 0.33 times 10 to the power minus 18. Good, so if you chuck that into a calculator, you should find around 2.0 times 10 to the minus 15 hertz. Good, absolutely right. So the frequency... Okay, good. So 2b part II. Draw an arrow on the figure to show a transition which emits a photon of a longer wavelength than that which is emitted in the transition from n equals 4 to n equals 3. So what does a longer wavelength mean for the energy or for the frequency? If a photon has a longer wavelength, what does that mean for the photon's frequency? Oh, that's fine. Yeah, you changed it to electron volts. That makes sense. Good, absolutely right. So for any wave, we know that the speed, usually written with a c, is given by the frequency times the wavelength. So if we have a larger wavelength, that implies a smaller frequency. which in turn implies that we should be looking for a smaller energy gap. Okay, so we look at this picture and we try and find a smaller energy gap. And of course, you can kind of see from the picture, and you can check using the numbers here on the right-hand side, that a smaller energy gap than the photon in 2Bi is this energy gap here. So draw an arrow to show the transition. Well, it's a transition from n equals 3 to n equals 2. And I should get the rest of this so we can see how the answer to the exam question would look, which would be just this bit. Good, so larger wavelength means smaller frequency, and that means smaller energy. Okay, final question. Figure 1 shows part of an energy level diagram for a hydrogen atom. When an electron of energy 12.1 electron volts collides with an atom, photons of three different energies, are emitted. On figure 1, show with arrows the transitions responsible for these photons. Okay, so we have to look at the picture and we have to figure out which energy levels would in principle be consistent. So what can we do? Has anyone got any ideas? Exactly. So you've just got to find the energy gaps which are less than 12.1 electron volts. So if we take a look here, well, 13.6 minus 1.5, that would be equal to precisely 12.1. Good. So we could definitely fall from here to here. This would be an energy gap of the right size. Now, of course, we could do smaller ones as well. So for example, we could be at n equals 3 and we could fall to n equals 2. Or we could be at n equals 3 and fall to n equals 1. Now we're told there's only 3 different energies being emitted. Now, that means that our electron can't be starting any higher than n equals 3. Because if it was starting any higher, then there would be even more energy gaps that could have been emitted. For example, this transition here. So we know it must be starting at n equals 3, and then these are the 3 energies that can be emitted. Okay, in 1 part B, we're asked to calculate the wavelength for the photon with the smallest energy. Give your answer to an appropriate number of significant figures. So here we're going the other way to what we did before. We need to look at the smallest energy of these transitions, which is the transition from n equals 3 to n equals 2. The transition from n equals 3 to n equals 2 has an energy gap size given by 3.4 electron volts minus 1.5 electron volts. And if you put that and that is exactly 1.9 electron volts. Now we want to turn this into a wavelength, and the method we're going to use is to use the fact that the change in energy must be equal to h times the frequency. And so the frequency will be equal to the change in energy over Planck's constant. And then we'll use the fact that the speed of light is equal to the frequency times the wavelength. So the wavelength would be equal to the speed of light divided by the frequency. Okay, if we put these formulas together, we find that actually the wavelength would be equal to c over the change in energy over Planck's constant, which is just Planck's constant times the speed of light divided by the change in energy. Now we know the change in energy, it's 1.9 electron volts, but we need to put it in joules. So altogether, the wavelength will be equal to Planck's constant, which is 6.63,
times 10 to the minus 34, multiplied by the speed of light, which is 3 times 10 to the 8, and then divided by the change in energy. And the change in energy is 1.9 electron volts multiplied by the conversion to get from electron volts to joules. And we know each electron volt is 1.6 times 10 to the minus 19 joules. So we can chuck all of that into a calculator, and you should get around 6.6 multiplied by 10 to the power minus 7 meters. And that's the final answer for the wavelength. Good. So there's a lot going on in the last one. There's a few more conversions and so on. Okay, so to round off the lesson, you should now be able to understand how electrons in atoms are organized into energy levels. You should be able to calculate the energies of photons emitted by excitations and then the frequencies and the wavelengths. And you should understand a bit about these experimental procedures where we figure out what a substance is made of by looking at its absorption spectra or by its emission spectra. Okay, so feel free to ask me any questions you have. While you are doing that, I'm just going to give you a look at what we're doing on the SnapRevise website. Because essentially we're doing lots of these web classes. We're doing about 4 physics web classes a week at the moment, including a couple that are a bit different to the ones we're doing here. So we do a couple like this, and we do a couple which are called drop-ins, where you can just come in and ask any questions you have about anything you're confused about, and we can go through them together. It's usually things like exam questions and so on. So there's a biology web class coming out next Sunday as well. So you should be able to see the schedule on the YouTube channel for those. Yeah, and as I was mentioning, we're doing 4 classes or so per week at the moment on the SnapRevise website. We're covering pretty much the full curriculum for AQA, EdXL, and OCR, including notes like the ones you've been looking at here. And I think they were posted in the chat as well, actually. Maybe Boris is already learning. Good, okay, so I'm just gonna take us out now and show you guys what we're up to so that you can see it for yourself. So, here you go. So hopefully, with any luck, you can see what is currently my SnapRevise account. I am lucky enough to have my own SnapRevise account at the moment where I can look at my own videos and so on, and lots of others as well. And if I'm signed into the website, as you could, now you've got the code to check out our free trial. You can go into tutoring, which is the stuff that I'm mainly doing at the moment. And depending on what course you sign up for example, I would of course sign up and take a look at the web classes we currently have going. So like I said, we've got 4 sessions a week on the SnapRevise website, which are basically like this session we did here. They're completely interactive, so you can ask any questions that you have, anything you're confused about along the way, and we try and go through them slowly and make sure that we're all understanding them. So the idea of this is to kind of do tutoring, but make it more affordable. So the idea is we're doing them in bulk. So you can buy per month, and it's £49 a month. And what that is that includes 4 sessions a week, including access to all of our online video courses and so on. There's 4 of these live sessions a week, 2 of them which involve teaching material, and 2 of them involve drop-in sessions. So the drop-in sessions are sessions where you can come in, and as I was saying, any questions that you have, you can just send me by email, questions that you can get through on past papers where you didn't understand the answers, and I can explain them to you with everyone together in sessions like this one. So like I was saying, we're doing lots of regular stuff at the moment. It's not just me, it's James as well. And as you can see, we're teaching, what do we have coming up? Well, here I'm about to do a session, in fact, exactly right now, on traces and ultrasound, and then a drop-in, and also some revision sessions on electricity. And then later on in the week, James is doing another drop-in and talking about electric fields. And we do more of these each week. So I hope this is interesting to you, and I hope I get to see some of you on there. Actually, it'd be nice to see some of you here today and go through some stuff with you on the Snap Revise website. In the meantime, I promised a code, so there will be a code. So if you enter this code at the checkout on the Snap Revise website, you can join us, and I hope to see you there. Great. So thanks very much, everyone, for coming. And yeah, hopefully see you at a session soon. Cheers for being so responsive. Makes for a good session. Do I know any good physics books? Not off the top of my head, but I do know the Snap Revise, the Snap Revise video courses are good. I'll let you judge. Okay. Cheers for coming, everyone. Thanks very much. Yeah, and stay safe. Bye.